right at the beginning of the project. And there you see the excavation, open foundation. You see rock at the location, and you see the unique nature of the foundation reinforcement. Also, it was a circular foundation. That's the rough layout, and you see the yard 1 and yard 2. We fabricated the entire arch on site physically. You will see pictures of these also, and that's where the arch went into place. These are the approach spans, nothing very spectacular about it. Like I said, 12.5 meter spans, 6 spans of 12.5 meters on one side and one on the other, making a total of 87.5 meters. So these were conventional spans. This is the solid approach on the Pune end, and these are those piers for which you saw the foundations, circular foundations below the large piers which support the main arch. That's another view of the solid approach. Now, we come to the actual arch and how we erected the arch, because that's the crux of the whole design, is how we had to work back. Of course, as you know, you do the whole design for service stage, and then the construction stage analysis is done only after the contractor comes in place. And so once the contractor was in place, we had to redesign or recheck the design for the way that the constructor was going to construct this bridge. And of course, I didn't mention that this bridge was executed on an item rate basis. So it was designed for the MSRDC, and the contractor executed it on an item rate basis. So what we did is to have these round piers that you saw. We had these pipe support for trestles being. We were allowed to do that because there's a simple weir, a KT weir just ahead of this bridge. It was easy to do this. And then on top of that filling that we did, we had these piles driven into the filling. What you saw as yellow dots here are these supports, which were like piles, steel piles, infilled with sand and topped with PCC, and then you had a steel sitting on top of it. So you will see pictures of these, and those are those piles that we drove. That's the filling that's done. Those are the piers at the end. So you see placing of the top portion of these trestles at the bottom of the trestles and the top of these piles that have been driven. So these are steel piles driven into the rock. Well, not into the rock, but up, resting on rock. There you see a picture of how the trestles are sitting on top of the temporary foundation. So that's the portion that you saw in the last picture. That's the trestle going up, a simple hydra being used to put the trestle up on top of those pipe location. These are some of the first beams going in place on top of the filling that we did. There you see the cross beams going into place after the main beam has been launched. And these are, you see the bottom booms, if I can call it that, the bottom boom of the arch. And this is the plate where the top boom would get attached. So there you see the picture again, the whole section being lifted and put in position. That's a picture during flash floods that occurred on the site. And you see that we have launched the first portions of the arch on either side. The bottom portion of the arch on either side, you see the shear connectors going in place along with the arch. Once the floods receded, then we started with the bottom boom. And this is where it became critical, because this bottom boom had to be now checked for an independent boom being lifted and placed in position and to span this portion. It was, of course, designed for a 108 meter span, but as a complete arch, not as an independent freestanding member. So each member that you see in this pictures had to be rechecked for their self-weight carrying capacity so that they don't bend. We did not want any bend in this structure. So some of these have been temporarily strengthened. Of course, when I say temporarily strengthened, it means permanently strengthened but not paid. What was paid was only the steel that was allowed in the final service stage. So some of these members had to be strengthened at the cost of the contractor. So that's another view. Again, we had to not only check the self-weight but also the slenderness, because that's also very, very critical for these members. You will see once it goes in place, it's very slender at this moment. That's the second portion. So these are some of the first beams. This is the second beam going into location. These are the longitudinal beams going into position. And mind you, you can see that the entire beam is fully prefabricated, which means that in the yard, not only did we do the beams, but we also put in the shear connectors before the beams went into position. And progressively, we put all these beams into position. That's another view, a long shot of the bridge. That's a view of those cross beams going into position. And it wasn't easy because you see this now going down and going to sit on this seat that is created for this beam so that it can be aligned perfectly with the main beam. That's another view of this, the scissor that we fabricated. He's banging it into position so that it becomes absolutely straight and can be aligned in position. That's another view of the central beam erection. The cross beams going into position, like I said, some of these are in position. You see one more going into position. That's a top view using a crane showing you all things in position at the same time. So this is the bottom boom. These are some of the cross beams. These are some of the longitudinal beams. And some of the beams are still to go into position. So that's the tie beam erected and supported on the deck. Now, once all the most critical item was to erect the arch, because as I showed you in one of the earlier pictures, the arch was being fabricated not very far away from this location, but it was being fabricated away from this location. It was not in this particular location. And the idea was to lay, well, you can't see it clearly from this, but was to lay these 4 pieces of the arch horizontal on the already erected grid, and then lift this arch into position so that it can be fitted exactly into location. Now, how did we do this? It's very easy on this. Now, that's a model that we created because what happened is when we were doing this bridge, actually, a lot of people who used to visit, the clients, some of the proof consultants, some of the contractors and consultants who came to see the work, could not imagine what we are doing. Everybody imagined that for 100 meter, it was too slender a deck because they could see only this going into position. So we created this small, what we are trying to do. And this was kept on location all through the work. So there you see, that's the fabrication in progress. That's how we started. Those were those plates for the arch. That's the arch going in position. You see the template at the bottom on which the arch is being fabricated. Those are pieces of the arch. And just like segmental construction these days for concrete, this has been fabricated segmentally. So all these arches are match cast, if I can say that, or match fabricated, if I can say that, which is what you saw in the last picture. So here you see you're fabricated as though it is match fabricated. So we created a 100-meter horizontal jig on site so that we could do this. That's another picture. Now that's the anchor plate on which the McAlloy bars were to be fitted. And you see the thickness of these plates. These are 70 millimeters. Some of these plates are all 70 millimeters. And the trivia on this, as you can see, is that every plate had huge amount of welding on it. You can see the layers of weld. And it was quite a task to do this weld because you cannot do this continuously for fear of warping. So this has to be done on a day, then you keep it for a day, let it cool, and then do the next layer, and so on and so forth. And then to do the radiography and all the tests, the dye penetration tests, etc., was quite a task. but you can see all the weld that has gone into these plates. That's just to give you scale. That's the man sitting there on top of this and welding. You can see the scale of this anchor plate that we have created. That's a view when the anchor plate was fitted on top of the bottom boom. Sorry, that picture is actually vertical, but it's come out horizontal. Sorry about that. That's the fork of the McAlloy bar. The McAlloy bars, of course, were imported. They're not manufactured in India. Even till date, I think we still don't manufacture these bars in India, but these were imported from UK at that time. That's the tuning for the McAlloy bars. Where the arch starts going into position. These are some of the first pieces that are being lifted and putting them on top of the grid that we have already done. That's the first segment of the arch, alignment of the arch being done. So you can see the scale of the arch. It's not very small, although every segment was quite light compared to the full arch. But okay, that's light is a comparative statement. Light and heavy is a comparative statement when you're dealing with 826 tons of steel. That's how it looked when the arch went into position horizontally on top of the erected deck. That's more of the segments going into place. These are pictures just to show you the scale of the whole thing. 108 meters. So imagine 54 meters on one side. Of course, it's longer than that because 108 meters is the linear length. The circular length was more. That's one of the first pieces of the arch going into position. You can see the three-dimensional effect of the arch. It's not very easy to be able to be sitting on top of this and doing alignments of these arch. It wasn't an easy task. These were the aligners which were created, the jigs and fastenings that we use. That's a top view to give you idea of what's happening here. So all that you were seeing earlier was a two-dimensional X and Y picture. So this gives you the Z scale of that picture. So you can see that this arch is now going into position. That's another view from the other side. More insightful people in the audience would have realized that we left this opening on purpose because we wanted to lift the arch through this opening. Otherwise, getting the arch to this position was itself a task, which is why these cross beams were not put into position. Arch portions were lifted through the hole that was created. There you see the arch through that hole going up. More of those arch portions going up even as water is let out below the arch. Now that's the trestle that's going up so that we can rest the arch when we lift the arch up. So as you can see, that's the first trestle supporting the edge of the arch so that we can lift it, we can connect it. There you see the effort being made to connect the arch. More pictures of the same thing. You can see the size of the crane. There you can see the model for people to see while we are working on the main bridge. So as you can see, even as the portions of arch were fitted, these beams were also put in position. The cross beams attaching the arch and aligning it and maintaining the position were also fitted in position. So that's the other side of the arch going into position now. And that's how it looked when all the four positions were taken. You see the person on top trying to align and finish off what we want to do. So now we start lifting the arch into position. You see now we're trying to lift the arch here on one side. The arch goes up. Now this is the most crucial part of that lifting. At this point, we wanted the arch to hinge because we wanted this point to go and meet here. At the same time, we didn't want this point to move. So this contraption that you see, jugaad, as you call it, innovation, I call it, was created so that we had a simple turnbuckle. You see the turnbuckle here, a simple turnbuckle holding a pulley and a chain pulley, so that we could align the arch perfectly into position. Because remember, what you're seeing is in 2 dimensions, but what we did on site is in 3 dimensions. So it's not very easy to align the arch. So there you see one more view of that turnbuckle and how that arch is hinging. These plates were put in position so that we could hinge the arch at that point. That's how it looked when the arch finally came into position and was welded into position. So that's an intermediate picture, and you see what we have done with the trestle. The trestle is connected at this position. So even as we lift this, the trestle moves here, and the arch goes up till it reaches a position where the trestle can be locked. There you see the trestle is locked into position so that the arch can be finally aligned at all 3 locations. That's one more view of the arch going into position. So once you had one arch into position, the other arch went up in the same manner. So you can see the crane now moving and going up with the second arch. So you can see the relative heights. 22 meters above the deck is where the trestle stops, and the crane goes up to 40 meters above that so that it can lift and still have capacity to be able to lift this. Of course, here the capacity, vertical capacity is not an issue, but the boom of the crane is an issue. That's a picture from the top showing you how that arch is supported and how it is hinged at that location. It's more pictures of the same thing. Now that's how it looks after the arch is completely in position, and we are now threading the cables. You can see the cables going into position. There you are, the cables are now in position. And like I said, these are not vertical cables. These are in the form of a network arch. So they are all inclined. And again, they are 3-dimensional. Each cable is 3-dimensional. So working out the lengths of these cables, getting them manufactured in the UK and bringing them here to millimeter precision was quite a task. That's how the final plate looks. Again, imagine this is in 3 dimensions. The plate has been fabricated in 3 dimensions so that we can fit this perfectly on top. Even a small kink can lead to a disaster and a catastrophe at this point. So it has to be absolutely perfect. Once all this was done and it was in position, we started laying reinforcement for the deck slab to be cast. There you see the deck slab going into position now. The concrete being poured on top of shuttering. This is the bottom view of the shuttering. That's once the slab has gone into position. And that's nearly a final view of the bridge before rest of the finishing work has started. But as you can see, the net arch is in position, the concrete is in position. That's another view of the shuttering being done for the arch, for the slab. The slab reinforcement. This is another interesting thing. On top of the pier of the arch. I'm sorry. This was well. This isn't really the tallest structure in the area, but okay, we did this as a precaution because it was already almost 30 meters above the water level. We were 22 meters above the deck to the bottom of the arch, but okay, we were still quite high above the water level. So that's the painting of the arch with the help of a crane, that's some more painting going on. And that's a final view of the bridge before we actually inaugurated it. A couple of points now which I want to make before we move on to the next bridge. The first thing is that one must know that when we did the design of this bridge, software like SAP, Midas, Sophistic, Lusas, etc. were not available, at least not in India. This design, remember, was done in 2003. It was done, most of you may not believe it, but it was done manually by Mr. D.N. Bove, my father. Of course, it was cross-checked by me on STAD at that time, and then IIT Mumbai cross-checked it again with their own version of SAP, which they had on their mainframe. And then the results of the manual design that was made with the computer results that we had was within 2%. We did a load test of this bridge, 1.25 times the design load, live load. And the design deflection was 110 millimeters, if I remember right. And the deflection that was physically measured was 85 millimeters. We had a near 100% recovery, 84.5. I still remember those figures, 84.5 millimeters recovery. And one of the interesting things that happened in this bridge is that once the bridge was inaugurated, there wasn't much traffic on this bridge on the time that it was inaugurated, because this entire road, although you see the road quite wide, the connecting roads were not yet in position. The entire road was just under construction at that time. It took another 2 years after that for the road to be constructed. But before that, for the 2 years that it was open to people, from 8th August of 2008 till about end of 2010, it was practically being used as a picnic spot because it was so beautifully lighted. People used to come there to spend their evenings, and it looked like Chowpatty in Mumbai. There were bhel puri walas all over the place and pav bhaji walas all over the place and all that. So it was an interesting end to a bridge. Well, that's how it looked just prior to inauguration, fully lighted, etc. The only thing that was not done on this bridge at that time is signature lighting. It wasn't illuminated because we didn't have a budget, unfortunately, at that time. 14 crores was already way over budget. Like I said, the original concept was to do simple 10 meters. And so the budget was only 6 crores or 7 crores or something like that. We were already 100% over budget when we presented this case. And of course, to end it all, this bridge won the most outstanding bridge national award in the year 2009, and Mr. Bide awarded us the certificate and so on. Mr. Jambekar, who was then in charge of the project management of this bridge, received this award along with Mr. David Philip, who was our director in India at that time from TPF. So that's about Pauna Bridge. Like I said, I haven't really talked about the design issues of this bridge. Couple of other issues that I must mention in this bridge is that this bridge was metallized. It doesn't have any special anti-corrosive steel or something like that, or anything like that. It has simple mild steel, carbon steel, if I can say that, simple mild steel. Of course, thicknesses we allowed for sacrificial thicknesses at that time, 1 millimeter on either side, or I think 2 millimeter on either side or something like that. So we had a 10%, close to 10% margin on that. But I'm happy that after 20 years nearly, well, almost 15 years, there has been no sign of corrosion on this bridge. I inspected the bridge, I think last year, just before the lockdown, I was there. There's absolutely no sign of corrosion on the bridge. It is in good condition. Absolutely no problems with deflections, etc. of that bridge. Okay. So from a basket handle arch to the Kengeri grade separator. And like I said to you, this bridge is not something that is ground shattering or something like that. This is a simple arch bridge, in my opinion. It's a simple bowstring arch. So why did we do this? So the junction of the outer ring road with Mysore-Bangalore highway, which was being 4-lane, was becoming a critical and a perpetual accident spot. It was a T-junction. So the brief that was given to us by the client was to come up with a solution to alleviate the traffic problem at the same time as allowing the Mysore-Bangalore highway to be widened to 4-lane with paved shoulders. So that's a view of what we thought we would do. That's the highway at that time. So it was 6 lanes here in this particular location. We simply considered 6 lanes because 4-lane with paved shoulder means 6 lanes effectively. There was an ROB here, existing 2 lanes of an ROB. And so the idea here was to connect the ROB to an arm which would go like this towards Mysore, bring the traffic coming from Bangalore wanting to go to the outer ring road on this loop, a U-turning loop, and connect it to the ROB. Bring the traffic coming from Mysore onto this arm and allow it to go to the outer ring road, effectively creating a complete interchange at this location. So no junction is required finally. This was conceptual stage. What you're seeing is a presentation that was made at the conceptual phase of this project. And you can see there are two structures that need to be created for this solution to work. So what we did is to propose two unique structures. One was what I call a fishbone structured bridge on one side. This is a fishbone structure, if I can call it that. So it's also an arch of sorts, not really a conventional arch, but an arch of sorts, three-dimensional arch. There you see one more picture of that. It's the shape of a fishbone. And on the other side, we had this arch, which was a freestanding arch, and you had a U-turn going through this arch. So this was something which could not be imagined at that time. Nobody thought that we would be able to produce a structure that could actually provide for two lanes, which could go through the arch and come out through the arch. Now, what you see here, remember, is conceptual. Ultimately, we did not get this land. We had to find a solution to stop this arch here because this land was simply not available. A lot of modifications were required to be done to this once the project went through, but the concept itself was accepted and approved. And what you see is different pictures of this concept which were presented at that time. Now, of course, because of the land problems, the client came back to us to say, okay, this arch looks a little flat. Why don't you modify the arch? So we came up with this arch, which was a different type of an arch. It wasn't a flat cylindrical arch, but was a more, well, this one is a cylindrical arch. The earlier one was a more of a arc than an arch. And the third one was a cable stayed U-turn completely suspended from an arch. This particular solution was quite workable. Actually, we started detailing this, but the client thought this was too revolutionary for their taste, and they said, "Well, let's do a simple." Yeah, that's the structure that we proposed, and they said this is too revolutionary. Let's not do too many things, innovative things at the same time. Let's go for a conventional arch. So we started work on the accepted concept. And that's a picture of the site before we were doing construction, and that's how congested it was at this location, because you had a junction here where all this traffic used to come and stop, used to take turns, and they used to create accidents. So that's another view of the bridge while we were constructing it. So that's the arch that we finally put in place, and I'm not going to go into too much details of how this was done, etc., etc. But just to mention, this is, to my knowledge, the only arch, perhaps in the world, where the bridge goes through the arch. It doesn't go in a longitudinal fashion, but goes inside the arch from the sides and comes out from the sides. And again, you see it's not a bowstring, it's a network arch. And here we have not used McAloy bars. Here we have used conventional pre-stressing cables. These are 2070-15 pre-stressing cables and grouted into position. There you see a view of that circular arch. You see piers on either side because we could not get land on both sides. And so we had to modify the design to get accommodated within the, and here you see the bus going inside, a bus taking a U-turn and coming out of the other side. So that's the unique nature of this arch. That's a closer view giving you an exact idea of how it goes in and comes out at the other end. So these are the stiffeners that we had to put in place so that we could hold the arch without any cables in this location. The cables are only in this location on this side and are the full width on the other side. So again, it's an asymmetric arch, which perhaps in my mind is completely unique. I have not seen an application like this anywhere else. That's the road that goes inside, comes out of the other end. And that's the bus inside of the arch. You see the bus traveling through the arch. This bus is turning inside the arch. And that's a loaded container trailer, That's also using the bridge, and it turns inside the arch. Just for your information, and just to mention, the 7.5 meter standard width of 2 lanes is widened to 9 meters inside the bridge to account for the sharp U-turning inside the bridge. So what you see here is 9 meters and not the conventional 7.5 meters. So it's easy to traverse this curve without accidents or toppling over. That's the view of the arch. Of course, we did the usual thing, load tested it and so on and so forth before opening, and we had very good results. That's on the other side where we were supposed to have the fishbone arch, which was also found to be too revolutionary by the client. And they said, well, let's go for a conventional bridge. And so we did a conventional widened slab on this side. Of course, it's an integral structure for the entire length of the curve. So that was also different from what we would normally have done. So that's the view on the other side. So that's about what I wanted to say about the Kengeri grade separator. I'm going to talk quickly about the Gandali bowstring arch bridge. And again, like I said, this is a bridge that's not unique in design. It's an 80-meter bowstring arch. But the way we launched this bridge is unique, and which is what I'm going to talk about quickly. I'm not going to spend too much time. So we call this the bridge on wheels. Why did we have to put it on wheels? I will tell you. So that's the location of the bridge. It's in beautiful Goa. It's interior of Goa. So that's the length of the bridge. It's a 400-meter long bridge in which, well, just to show you, it actually crosses the river only at this location, but this is all backwater of the river and marshy land, so we had to put a bridge here. But the main bridge is here, and this is a navigational channel. There are barges plying in this all day through, so you cannot stop this navigational channel at any time, even during construction of the bridge. So we could not stop that. So that's the location of the bridge. That's the Gandali bridge site. That's more of the view, and like I said, that's the arch, and on both sides we have conventional simply supported spans. The substructure is wall type pier, so I'm not going to go through too many details of this because this is nothing out of the ordinary. This is conventional. What we did here is conventional. So here you see what makes this project unique is the 250-ton steel prefabricated arch. It's 80-meter long and 16-meter height of 16 meters because you need 14 meters clear because of the waterway. So it's at 16-meter height, which has been lifted, moved on wheels and on a barge and finally placed on the pier. So the entire process took 21 days and is perhaps one of the rare bridge building procedures in the world. At least in India, this is probably the first time that somebody has attempted to do this. So this was the gap that was to be bridged with an arch span, and this is a navigational channel. You cannot stop this channel at any point in time. You can take traffic blocks like you take for railways, but you can't stop it. So these were some of the agencies involved with the project. GSIDC, Goa State Infrastructure, is the owner, Singla, contractor, SN Bobe Consultants, Kamath Equipment Services, the fabricator and freight wings, the people who lifted the bridge. So this is conventional, again, fabricated arch elements. We knew how to do an arch. That wasn't very difficult. So we did the whole arch on ground in the approach. So the arch was completely assembled in the approach. Now this is the arch fully fabricated, but you will see that in place of the HT bars, we have put pipes. Okay, so this is on the ground in the approach. Now the task was to pick up this monster, lift it to a height of 16 meters and roll it into position and then roll it back once, because this is by the side of the bridge. So roll it back into location on the bridge. So what we did is we got what are called SPMTs, self-propelled motorized trolleys. These are these SPMTs, and they have three-dimensional movements, which means you can move them in the X and Y and in the Z direction. So in the Z direction, they have jacks and you can lift them. You can lift loads with them also. So we had these SPMTs which we brought to move this bridge. So what we did, the first thing is that we brought these SPMTs and inserted them below the fabricated arch. And then we started lifting the arch. Remember, we have to lift this by 16 meters. So the self-lifting capacity of the SPMT is only 600 millimeters at one time. So we had to jack them up and place them temporarily on this, and then put a crib here on the other location, and then lift it at that location. So what you see here is the actual lifting of the so that's the hydraulic jack that lifts by 600 millimeters at one time. That's part of the SPMT. So there you see, we have now lifted it by what, 1.2 meters. We are now placing cribs here so that we can switch the loads between the two. So that's after 1.8 meter lifting, and you see it's being lifted now. We have to lift it up to here, up to 16 meters. So this is from the deck already cast on the top, and then we are lifting the arch to this height. So the lifting of arch was 24 hours because we wanted to finish it as fast as we could. That's the lifting of the arch fully complete. So you see these trestles that are created after we have lifted it fully. On the SPMT also there are trestles so that we can move the bridge, sort of march the bridge, if I can call it that. So we created a tower on top of the SPMT, loaded it on top of the SPMT. So you have these two and these two, 4 SPMTs, which would pick up this structure and roll it into position. So there you see, these are SPMTs, and these are the towers that we created so that we could lift. That's the cross beam on which the arch is going to be lifted, and that's the pipe that we fixed on top. Transfer. That's also the SPMT going in position. You can see the XY of the SPMT. It was moving longitudinally and now moving transversely. So you can move SPMT in all directions. Once the tower goes in position, the other cribs were then removed so that we could march the truss, the arch into position. Removal of the crib supports. Now what we did so that we could move this is we brought in a barge and placed it along the arch. We took a block of about 3 hours on the navigational channel. No barges were allowed to ply during this time. For an 8-meter opening of the river, we had the barge is now in position, and we are going to roll this on top of the barge. So that was the strengthening carried out so that we could roll it. That's the aligned barge. It's now ready to carry the arch. That's the winch that we placed on top of the barge. We welded it on top of the barge so that we could pull the arch into position. So it's ready to roll on wheels. It's rolling on the ground, and you can see it's actually cantilevered on both sides, and it's rolled only with the help of these 2 SPMT towers. So it's on the jetty nearing the barge. It's now on the barge, as you can see. It's physically on the barge. And on the barge now, all that we needed to do was to shift the barge sideways into position. So it's on the barge. So we had winches to go into position, and you can see the structure side shifting on the barge coming into location and into position. Once it is in position, then lowering onto the barge on bearings was done using jacks. On this side, you can see the barge has now gone out, and we are now lowering it onto bearings. It's almost at the final location. That's the final position of the arch. And then, of course, you see here the jacks which were used to lower onto the bearing. It's final positioning of the arch. That's how it looked once it was completed. So like I said, this is more of a construction method of the arch than about the arch itself. So we have seen 3 different arch bridges. The 2 arch bridges that you have seen, second and third, like I said, are not ground shattering in their applications, but definitely unique in the way that we have launched it in this case, and the way that the traffic moves in the earlier 2 cases. We come to my final arch bridge, the steel arch bridge at Bhopal. This is an actual photograph of the bridge just prior to inauguration. The first bridge you saw is 108 meters, whereas this bridge, excuse me, this bridge is 150 meters main span basket handle bridge. It's got 2 into 25-meter rider spans PSC girders on both sides that you can see. And you can see one span here and one span on the other side. So we have these one span on either side, so 2 spans. So we had 150-meter main span. So this, having done a 108-meter span in 2008, we had the confidence to do 150. So we did a 150-meter arch bridge. But what's different in this is the way that we created the arch, and that's interesting to see how different it was. So again, as usual, we start with the soil investigation. We do the piling. Of course, here we used a piling platform like they do for jetties, because this is in a lake, it's not in a river. And of course, this is now almost standard for all fabrication units, the gas cutter, the roboplasma cutting, the semi-automatic saw, the drilling machine, and so on, computerized drilling machines. And now you see here the jigs that are created. Like I said, we already had the experience of creating 3-dimensional arches, so we knew what to do this time around compared to Pavna, where we did a lot of research and development to come to these solutions. So that's the fabrication and the mock-up that was done, the fabrication of the arch being done. That's the mock-up being done, and you see the arch fully mocked up in the fabrication yard, not on site. This is unlike what we did at Pavna. So this was done far away from the site. So that's the arch in position and the testing of joints, etc., being done on site. So we did all kinds of testing. The cable suspenders in this case have come from OVM China, and you see them being tested in China. So the arch itself, 150 meters, a height of 30 meters, and a weight of 1,000 tons in this particular case. The weight of each segment varies 10 to 13 tons. E350 steel being used. Plate thicknesses varying from 32 millimeters down to 12 millimeters and so on. So here, like I said, we used a different method of erection of the arch. So this is the final platform with temporary piles, which is ready for erection. And mind you, we use the same technique for temporary piles that we had used in Pavna, which is steel piles and simple sand filling with PCC topping. So this is the methodology of the bottom girder being launched. So we simply place the girder on these piles and push it with skid rollers into position until all the girders, all the bottom boom is in place. So there you see the total segments at bottom, girder spacings, etc. The girders going into position on skid rollers. When I say girders, I mean the bottom boom actually. There you see the bottom boom being pushed into position. And it's not easy, 150 meters, but like I showed you already, a mock-up was done. So we were pretty sure of what we were doing and how this is going to be launched. So that's the cross beam, all beams in position. So here what we have done for the arch lifting. Of course, here we knew what we were going to do. We didn't have to hinge it here, etc. We got a heavier crane and then placed it in position. So there you see, we put trestles, we put the first segment into position. You see the crane that's being used is not the conventional crane. This is a contraption that we made so that we could start lifting these into position. So there you see the arch goes into position slowly. And what we did here is to actually create trestles as we move along, because we had this contraption to lift. So it was pretty easy to do. There you go. That's the second segment in position, third segment in position, and so on and so forth. The entire arch was in position. So we did 150 meters of this arch with a simple contraption like a crane, and then we had trestles going up all through till we had all these cables strung and fully stressed in location. Deck slab was cast after that. The total time that we needed for the launching of the arch is 145 days, nearly 5 months it took for us to get the whole thing completed. Fortunately, here we had a budget that the corporation allowed us to do illumination, and these are uh, some of the ideas that we used to do illumination. And the arch has been illuminated using similar kind of ideas that you see here. That's an actual picture of the illuminated bridge. So you will see that we have illumination here, which is of a signature type, making the bridge look very, very beautiful. That's it. That brings me to an end of the presentation. Thank you very much for a patient hearing. And I hand over back to the moderator.
Thank you very much, sir. Thank you very much, uh, Atul Bhobe, sir. Thank you very much. I think now let me request to our president, Vinay Gupta ji, to give his initial comments. And Vinay Gupta ji.
Oh, yes, yes. Thank you, Dr. Gopal. Well, not only comments, I'll say much more than the comments, if you permit. A bit about IIB, I know you saw this film on IIB or whatever we call it just now, some video. But let me tell you in my words that IIB is the largest professional body engaged in bridge engineering, dissemination of knowledge, no doubt. It started in 1989 with a few hundred members. And Mr. MC Bhide, of course, you saw his picture. He was the founder, along with Mr. Bhobe, also was more like founder in 89. And it has grown from those few hundreds to about 7,000 members now. And absolutely the people who are interested in bridge engineering. So that is how this organization has been. And of late, we have made some changes to the structure of IB. But let me not bore you with all that. Very recently, IIB has purchased an office space in Andheri East, that's Mumbai, because Mumbai is the head office of IIB. Very soon, we are going to have also some awards coming in. Perhaps in December is what we are planning, given the COVID conditions. Let's see what happens. So we'll be having that. My request to everybody is that please become members. The state question is, why should I become a member? I can watch all these programs by paying 200 rupees. But friends, the fact is that when you become a member, you start getting more and more information of the activities that take place. And when you get this information and you attend the activities, you get more and more enthused with the things that go around. So it's a whole group that works together, group that consists of you, group that consists of the members who have the kind of a drive to learn more and more through a society that is generated. Whereas if you are not a member, you may not have that level of drive which is required for you to grasp everything. So from that point of view, I must say that please try and become a member and participate in the activities and give us the enthusiasm to continue with the activities. Coming to the panelists, we have chosen for this topic of arch all the panelists as arch. Now let me tell you how. Engineer R.S. Sharma, he is the convener of the subgroup of IRC dealing with the arch bridges. So we have Arch with us, and of course we'll hear them in a while. Mr. Rajiv Ahuja, he used to run a consultancy called Arch Consultancy. So one more Arch and Arch. And of course we have others, Mr. R.K. Goel, Mr. Dr. Harshvardhan Subbarao and others. We requested Mr. Atul Bhobe to kindly speak on arch bridges and add a flavor, a tadka of cable supports. But he did the reverse. He rather gave us a bonus, a feather in the crown by saying that all of it is cable supported arches. When it comes to cable supported arches, there are two ways. One, that whatever he saw, which is that you suspend something, the deck, from the cables, from the arch, through the cables. The other is that you construct the arch. That time you use cables to support the arch construction. That's called stay cable supported arch, wherein you remove the cables and all later on. And of course, you have another set of cables like you saw just now for supporting the deck. So I think we've had a fantastic lecture today. And this time onwards, we are thinking that we'll not only have a lecture, we'll have a panel discussion. And this panel discussion should be a combination of our question answers, that we have 11 questions today in the QA box, and the discussion by all the eminent panelists, and of course others who are also joining voluntarily. Just talking of future, we are planning for the next lecture. I mean, now the coming away from the forms, let's look at materials. So we are planning our next lecture. Uh, we still have to finalize though. It may be on the Friday after next on reinforcement couplers. I have still seen that half the people do not know the use of reinforcement couplers. On the other hand, we have used millions of reinforcement couplers. And apart from reinforcement couplers, we will also have things like glass fiber reinforcement bars. Now, recently, but of course, in all these metro structures that you see, the underground ones, in most of them, we have a something called soft eye. Soft eye is a round shape, about 6.5 meters diameter in the diaphragm wall or in any wall that we have. And when the tunnel boring machine comes, it is supposed to cut through it and enter the station. So glass fiber reinforcement makes it easy to cut because its shear strength is low and you can cut it. On the other hand, glass fiber reinforcement has high durability, almost inert. And I have heard of a project where people are contacting me is that to design a vehicular underpass with all glass fiber reinforcement rods. So that's another new topic, new material that has come in, maybe new to India and not so new to the others. So we want to have this. And please feel free to suggest in the question answer box or chat box as to what new topics you would like for this series to continue. We have reached 17, 18, 19, all that number, and we want to continue with 100 and over 100. So with these words, I will wish everybody all the best, and we'll have the panel discussion now. So I request Dr. Gopal Rai to please take over the stage.
Yeah, thank you very much, sir. And to make my life easy, with us, Dr. Harshvardhan Subbarao, sir, from Construma, the managing director of Construma Consultancy. He is there, and he is one of the world famous the consultant for the arch bridges. So I request with the folded hand to Dr. Harshvardhan Subbarao, sir, to continue with this the big responsibility. Over to you, sir. Please.
Thank you, Gopal, but by no means any world famous at all. Just a fledgling consultant, that's about it. Atul, I just want to thank you. This idea that we had of this talk, it's turned out to be fabulous, and your stress on the fact that it should be construction driven, it showed to our audience and to the youngsters in the audience the importance of erection and fabrication and erection, and how important they are to get the jigsaw puzzle right at the end of the day, and how construction actually drives your analysis. These are all of them were cases where construction really rules the design, and how important construction stage analysis is for us to take on. It is an absolutely fabulous presentation and showing a lot of innovation. So much innovation that you displayed, each structure being differently put together and erected. I think that was quite amazing, and that you did it at that time when our codes, for example, our very own codes, we don't have a guideline for arch bridges, especially for steel arch bridges. At the time, all these are built and in service and doing well. So we have yet to come up with a guideline, and Mr. R.S. Sharma, as you see here on the screen, he is the chair of that committee, and he will be discussing where they are and what they're doing shortly. But what I found so challenging and innovative was, without any guideline, without any code, you could address most of the issues such as buckling, buckling of the arch instability, in-plane instability and out-of-plane instability are so critical and crucial to the design. It's not only the local buckling of the member, but it's the overall instability of the arch in plane and out of plane, which has to be controlled, especially when the web members are simple, flimsy suspenders, which are tension-only elements. So I think that is something very, very unique, which you have showed. I would like to ask Mr. Aresh Sharma to speak a few words. 1 second. Sharma Sahab, you go ahead, sir. Sharma Sahab, please speak. Sharma Sahab is the chair of our guideline for arch bridges in the IRC. Mr. Aresh Sharma from Sugam Technology, sir, please speak.
Thanks, Dr. Subbarao, and also Mr. Vinay Gupta, firstly for inviting me to be a panelist for this beautiful presentation. Is very nice. See, this I have been actually fond of this arch bridges right from the beginning. I have been in the ministry right from 1972 and visited a lot of countries. In 85, I went to US and I looked at the arch bridges, very long arch bridges. I forgot the name, but it was there, very long steel arch bridges that was there. But what I was finding is we are not using much. These are the most elegant structures. Everybody knows. And earlier times, arch bridges were used. Now the technology is diminishing. Only what you presented means only sophisticated arch bridges are being designed, only a few locations and constructed. But majority of the arch bridges, their applications are there, especially in hill section, say the northeast, okay, where the foundation and substructure sizes could be reduced, and these can be economical also, and maybe for medium span, for medium span bridges, culverts also, precast arches can be constructed. So we thought the importance of the arch bridges. What we found in IRC that we were not having any guideline for arch bridges designs. That's one thing. Other thing is, we have to demonstrate. And I wanted for this today's presentation, of course, time not much. We should discuss how to bring out the uses of the arch bridges in more numbers. See what we should do, what efforts, what is lacking, why we are forgetting arch bridges. Because they are most economical, they are the compression members only, no tension involved, isn't it? And then you presented lots of this thing. We are putting in our code, we are making a guideline that includes construction also, construction aspects. So we have included most of the types, and Mr. Vinay Gupta is preparing the chapter, and we are requested for the photographs of the technology involved, techniques for construction, and maybe the methodology part also. I'll suggest Mr. Bove to share with Mr. Gupta the methodology and some photographs, which we can put in the code.
Certainly, sir.
So this is actually my idea. I want the support from all of you who are in the field of the arch bridges. Let's bring out a beautiful code so that we find the more use of the arch bridges. We are covering a span up to 200 meters. So most of the spans or types, even network type, everything will come there, except for the very large spans. So that is the scope of our documents what we are preparing. I think with this, I'll hand over to Mr. Aswadan.
Thank you, sir. Thank you, sir, for stressing the need for the guideline, which is long since overdue, and we are all working at it. The guideline, as Saab said, will cover all types of arches, masonry to steel composite to steel to concrete, all of them. May I ask Mr. Rajiv Ahuja, a very senior consultant, who had a company, as Vinay said, called Arch Consultants, a legendary firm. It used to do wonderful structures. We worked together on 2 structures in Bombay, us as proof consultants and them as designers. And there were some awards that we got, if you remember, way back in IIB formation days, Atul.
Yeah.
We used to have those award sessions, you know. Ahuja Sahab, your views and comments, sir.
Thank you, Harsha. See, coming to this arch name, I remember late SP Chakravarti, you know, he wanted to construct an arch bridge by using stay cables, by, you know, erecting towers at the end and by using stay cable. That was Solding Cut Bridge. And we were inspired by one international conference where somebody showed us, you know, how the arches are constructed outside. And he was very much inspired. And in a tender, he put this condition that this has to be erected only by this particular method. And being a consultant, we did, you tender stage services. And this name of arch came from there only. So whenever this arch name comes to my mind, I always remember late SP Chakravarti. So that's a interesting story. And in those days, soldering third, of course, was constructed not in concrete. He wanted to construct in concrete. It was in steel. And then subsequent to that, I remember Ramshila Bridge constructed by Demons near Kullu. It's a very, very beautiful bridge if you have gone to Kullu. And then we have come a long way. Now we all know this Chenab Arch Bridge, which has got a span of 467 meters, height of 359 meters, constructed by, stay cables. In fact, when I saw the title of the presentation, I thought Mr. Bhobe will show the arch is constructed by, cantilever method using stay cables, but this is totally something different. And I remember Godavari Bridge. When Godavari Bridge was under construction, it was again constructed by using stay cables and tower. I went to the site and I went up the tower. The tower was more than 30 feet. And when I was, climbing, my arms started aching. And when I reached the top, I thought I will fall down. But somehow I reached the top and saw how they were stressing and all that. So I have a long relation with arch bridges, and in my company also we designed some arch bridges. I designed some bridges in Malaysia, Boasting Bridge, and another arch bridge near Mandi. So I will just talk about some important design aspects in arch bridges. Mr. Bhobe has shown, in fact, 4 bridges, and for me, each was a thriller. It's a movie, a thriller. Each one is constructed by a different technique, and it's a very challenging technique. Once you see the finished structure, you don't even realize how difficult was the erection. So each and every bridge he has shown is very, very interesting, and thanks to him for highlighting and showing us the construction techniques. See, during erection, we have to be very, very careful against wind forces. See, when you are erecting, the steel arches are very, slender members, very light members, and these are erected on trestles. And sometimes we don't take care of proper bracing of trestle in both directions. If we erect a very high trestle and, assemble our arches over there or whatever method we adopt, we have to be very, very careful of the wind. God helps us. Otherwise, due to wind, many girders have also fallen down. So we have to be careful. And in detailed design, as Dr. Harsha pointed out, the slenderness ratio is very, very important. See, if the arch is not properly braced, then the entire length of the arch acts as a effective length. That L by R becomes so high, it becomes difficult to manage. So wherever the clearance of 5.5 meters is obtained, we should heavily brace both the arches. Very, very important. British code gives some guidelines how to do it, but we have to be careful. People who design arch bridges for the first time, they don't realize this. They think the L effective length is between 2 bracing. That is not correct. We have to be very careful. Second is the connection. A couple of boasting bridges have collapsed also, failed also. And I remember one case where I will not name the bridge. The bottom chord is a box section and arch also is a box. And then you have a I-shaped suspenders. Now, how do you transfer the load to a box section from an I shape? And if you just put one gusset on both sides without designing it, it will fail, and it has failed. So one has to be careful about connections between top and bottom chord. And then where the arch meets the bottom tie, it has an inclined direction. The thrust is inclined, and it can be resolved into 2 components. The vertical part goes directly below to the bearing, but horizontal creates a sliding of the arch. So that one has to be careful. One has to design. If it's a steel bridge, and the bolts have to be designed to take that shear. And if it's a concrete bridge, then reinforcement has to be connected properly. So I think design in arch bridges is very, very important at both stages, during construction as well as during detailed design. And today we can boast of Chenab bridge, and I think someday somebody will present that bridge. It's all over on YouTube. Very, very interesting bridge, very challenging bridge. The span is 467 meters. It is designed for a wind speed of 266 meters per kilometer per hour, which is really, I have never heard of this kind of speed, wind speed for any of them. Thank you, Mr. Atul Bhobe, for showing us very, very interesting erection schemes. And we hope you continue to show us similar bridges in the future. Thank you.
Thank you, Ahuja Sahab. Very pertinent comments. That is good pointers for us all.
Dr. Harshvardhan Subbarao sir, this is a light moment for Atul Gobe sir.
Go ahead.
A short शायरी for Atul Gobe sir. पहले लोग नाम से बुलाते थे, आज लोग मुझे काम से बुलाते हैं. Thank you, sir. Atul sir. That's a good part.
क्या बात है.
If I'm allowed, I'll take some few questions from the audience. Would that be okay?
Please, sir, please.
Right.
What I suggest, Dr. Harshavardhan, the questions are there in the QA box, right. And I think all of us are free to sort of reply to the questions.
Right.
And while replying to the questions, the audience may come up with new questions, and that also should be honored.
Okay, so shall we not take those questions?
Yeah, Harsha, you take some, and any other panelists should be free to further comment on the answer.
Okay, I just Mr. Dhawan, Dr. S.K. Dhawan asks, what were the corrosion prevention measures and any structural monitoring during construction and post-construction? In general, that's a general question. Atul, quick response.
So for corrosion monitoring, like I mentioned, there was metallizing done to all this, because at the time when these bridges were done, RDSO had just come up with the idea of metallizing the structures. That was the only easily available corrosion protection system at that time. To do anything more than that, well, there was no state of the art at that time. The state of the art was metallizing. So metallizing was done. Almost all these bridges that you've seen, metallizing has been done. So that was corrosion protection. For SHM, there was no provision at that time to do any kind of structural health monitoring. I mean, SHM is becoming popular only today after people are realizing, albeit a little late, I would say. But okay, der aaye durust aaye. At least people are realizing now that you need to monitor your structures. You can't just say that a baby is born healthy, it will remain healthy for the next 100 years. It won't. You must service the human body. After it becomes 20, 30, 40 years of age, you have to go for annual checkups. The same way the bridge has to be checked up every year. The railways have a fantastic system of inspecting bridges, and it's been there for years together.
Very true.
The highways unfortunately don't. So that has to be done. And I'm very happy that people are asking questions about SHM.
Very true. Very true.
May I request Engineer Ravindra Goyal to say a few things about structural health monitoring from railways.
Thank you, Vinay. Thank you for giving me this opportunity. Actually, as Engineer Bhobe has rightly said, Railways has got a well laid down system of annual inspection of bridges. It's a fantastic system. Nothing can go wrong without the knowledge of the administration. So administration would definitely not like anything to go wrong. So road authorities, they have to come up with that kind of a system, and it's a Herculean, it's a very big task, I would say. It's a big challenge. If somebody can do it, I think it will be a game changer. And if you do that, I'm sure there won't be any requirement of structural health monitoring or the instrumentation which the people quite often talk. Because that is the stage when you put the bridge on in ICU, I would say. You don't want to move the traffic on a bridge which is practically on instrumentation, because that is not going to stay for long actually. You can sustain the traffic for a few years, but ultimately you will have to come up for a new bridge in Y-Set. So that is a very late stage. Before that, you have to do the regular checkup and then go for OPD. If necessary, a short tenure of, say, hospitalization, come back healthy. And then if you are in ICU, in that stage is when you have got only 20% chances of coming back. So I would not like anybody to go into that stage, or no bridge should go into that stage.
Sir, so we'll call you Dr. R.K. Goyal now.
Okay, thanks Ravindra. Now Sandeep Patiwar asks,
thank you.
What was the maximum weight of each piece and the capacity of crane used in Pavna, where the very innovative erection technique you have, keeping that center part absolutely blank of cross members, of cross girders, so you could do the erection with the crane through that gap. So what was this weight of each piece and the capacity of the crane used?
I'm scratching my head.
Roughly,
The segment weight was varying. I remember from 13 tons to 22 tons.
Right.
Capacity of the crane, I'm not too sure at this stage. I'm not too sure.
Right. Fair enough. Then Amitabh Ghoshal, who's the convener of our Steel Bridges Committee of the IRC for many, many years and a legendary steel designer of bridges, there would have been secondary bending in the bottom chord due to self-weight.
Yes.
And the deck weight. How was this taken care of in the design? Self-weight and deck weight giving rise to secondary bending in the bottom chord. How was this taken care in the design?
So I mentioned that briefly, when we did the service stage design, this was not considered because it was not originally envisaged that the contractor would come up with a construction scheme like the one that you saw. But once that scheme was finalized, we went back, we checked this, and of course there were in-plane bending and things like that. And members were simply strengthened to account for that. I mean, we had to put additional stiffeners, we had to put internal plates, and so on and so forth. So like I did mention that during briefly, I touched upon that to say that, that was not paid for because that was because of the contractor's scheme that, but of course, that's more contractual than anything. But technically speaking, yes, there were such stresses and they were taken care of by putting additional stiffeners.
Yeah, wonderful. Wonderful. Just to alert all the audience again to another very important takeaway point, that steel structures are very sensitive to what we call tolerances and initial imperfections. Okay. And it is impossible to get plates which are straight and clean and absolutely dead plane. There's always some geometric deviation when you manufacture. There's always some geometric deviation because of its height. So we have what we call geometric imperfections and material imperfections due to the welding process introduced. And that introduces a whole gamut of buckling phenomena due to imperfections at the time of construction. And these have to be taken care in a design. So that's just another point I wanted to add. Okay, Ghoshal Sahab again asked, was there any attempt to reverse the deformations before the maximum tension happened in that case, So I think you,
no, there was nothing made, and fortunately there weren't too many deformations of that type. Whatever deformations were there were within the design tolerance limits, so we had no problem with that.
You're right. This is a very interesting point. Vivo 1601, I think that's the phone he's using. I just want to read to amuse us all and to give him encouragement. As a fresher structural engineer, asking one question that here from among great engineers. Anybody can give me internship because in India, few are interested and some demand lakhs of rupee. Only that's why I paid for this webinar. I know jobs are less, but teachers would be less for us. This is all bad for new generation. Please help us. I'm extremely sorry to say, dear sir. So Mr. Vivo 1601 1606, please don't be anonymous again. You have amongst us engineers who would very happily take you for an internship if that will help you. Call any of our companies tomorrow and I'm sure we'll accommodate you if you want to grow. We are here to help. And don't feel any way that you will not get an internship. We will all give you all internships. I can assure you that from all the panelists here. So take courage and strive for better work. We are there to help and support. Then Rajesh VK says, very nice presentation of arches, very challenging and awesome. Subhash Ganguly, dear panelists, we would also like to hear about anti-carbonation coatings, bearing grouts, protection of bridges from weathering effects, water and chemical. I would say that this can form a separate topic for a seminar and a webinar in itself. But Atul, you want to say some few words?
Not really. I mean, the topic that I took up was not really in this line, but I think IIB would be happy to take up topics like this. I think this is more in line with the suggestion to Vinay. Vinay made a request to all the audience to send us suggestions. I think this suggestion is more in line with that. So I think we should take up that as an executive committee member. I would say in the next meeting, we can discuss this.
Yeah, I'm already receiving some suggestions and I have been replying to those suggestions. Like one of them was about bridge failures. Yeah. Remember we had a full-fledged workshop one day about a year ago. Right. So we can have such lectures also.
Right. Now, whether connection of vertical hanger and bottom chord and top chord of arch structure has been designed as a rigid or a hinged one, Atul?
This is a hinge. It's a hinge.
You might tell them a little more, na? That the end connection. How
well, if you look at the Gandali March bridge that I showed you, well, what happened there is very interesting. In fact, when we fabricated the arch, there was no out of plane deflection, I would say, or a horizontal deflection, if I can call it that. When we put those pipes, etc., it became a very rigid structure when we lifted it and placed it in position. So we lifted it, we placed it in position. Then we cut off. I mean, you put the vertical hangers in, and then we cut off those pipes. A very interesting phenomenon that we observed in this particular bridge, that the bridge actually moved. It actually curved in the horizontal direction by almost, I think, 100 or 100. Alok might be able to tell you, because Alok worked on the rehabilitation, if I can call it that, rehabilitation scheme for this bridge. And it created a scare, the bridge is moving in the horizontal direction. So what had actually happened was that because we created a rigid structure and then suddenly released all the forces, the structure actually moved under that load. But Alok was there involved in that.
May I request Alok? He is here. I can see him to say a few words about what he did.
Alok, are you here? Go ahead, Alok.
Yeah.
Yeah. Thank you. In fact, I was eager to chip in when Dr. Subbarao mentioned about initial imperfection. And he was absolutely on the spot. I mean, the Gandali bridge, which Atul has shown, that had some initial imperfection issue, because of which, you see, in an arch bridge, particularly in a steel arch bridge, the initial imperfection has got a sort of a significant impact, because the arch member is in compression, and if there is an initial imperfection, the axial compression actually accentuates that particular eccentricity, and that becomes a problem of buckling, particularly in the lateral direction. And that was precisely the problem in Gandali bridge, which at the time of, Atul will remember that at the time of inauguration of this bridge, some photographer noted the slight tilt in the arch in its own plane. And the next day, newspaper report was that it is a leaning arch bridge of Goa instead of leaning tower of Pisa. It was a leaning arch bridge of Goa. But anyway, the problem was solved by strengthening the bracings. Of course, we could not restore the original, sort of verticality, but the problem of further tilting was stopped by strengthening the bracing. Few points which I would like to highlight about the arch bridges, particularly the steel ones, is number one, our steel bridge code actually do not have any provision whatsoever for arch bridges. In fact, it is excluded. I think considering the fact that there are so many arch bridges which are being actually, executed, and Atul has shown excellent few arch bridges, and there are plenty others which are being done. Bowstring arch bridge is very common. So we should definitely include in our codes some additional aspects related to buckling of arches, etc. And one more very, very important thing in particularly this bowstring arch with suspender is the issue of fatigue checks. Yeah. And most of the designs which I find is that fatigue check people don't do, because probably it was not there in the previous version of the code. The current version of the code has got a fatigue clause, but probably people are not much aware of the fatigue clause. Particularly in a suspender, the stress range will be very high because the live load has got, particularly the connection of the suspender with the bottom chord or the top chord. If you really check the welding for fatigue, you will find that all the, majority of the cases, the welding is in a bad shape. I mean, it will not be passing. Wherever I have reviewed the designs, I found this to be a problem. And the third aspect of bowstring girders, we have recently rehabilitated two bridges, bowstring arch bridge ROBs in UP, which failed just because of the poor detailing of the box, top chord and the bottom chord. And that is, though it was an RDSO standard design, but even in the RDSO design, I found a lot of problems, which we in fact interacted with RDSO, and subsequently they modified the RDSO drawing, and the latest drawings incorporated many improvements from the as compared to the previous one. So short and sum and substance is that I think arch bridges, as Mr. R.S. Sharma mentioned, are definitely very aesthetic bridges. They are we need to see more of arch bridges. So IRC must come out with a guideline quickly under Mr. R.S. Sharma, and all these aspects must be covered very well, so that a common designer without much experience should be able to be guided by the codal provision, so that he is not going wrong. Thank you.
Why don't we add a little bit?
It was an excellent presentation by Mr. Bhove. I must congratulate him for this, and we would like to hear similar presentations more and more from him. Thank you.
I think all of you know Alok Bhaumik. He has a company called BSEC and is one of our most famous bridge design engineers in this country. Actually, you're seeing the most famous here only. These three fellows are more or less the most famous in this country, I would say. Okay, let me add to what Alok says, the importance of initial imperfection, the fact that we don't have it documented in our codes, the fact that fabrication tolerance are not there in our codes, the fact that we don't have a guideline for arch bridges. And now how do you deal with geometric? Suppose even you had it, what do you do, you know? And the importance of the end portal. The end portal is where the effective length has to be controlled. It affects both in-plane and out-of-plane buckling. And the end portal, the rigidity that is given in the end portal, and if you can do a simple thing like strengthening where the arch and the bottom boom meet, if you can make that point of connection very rigid, it cuts the out-of-plane effective length. Similarly, you put a bracing in the first portal at 5.5 or whatever vertical clearance you put your first cross member in the arch, that should be very, very rigid. Then if you do your eigenvalue analysis and you do your buckling check, you will find that N critical will be so high that it can never happen. This is elastic critical buckling. Then you go to a nonlinear. You take the first few modes, out of plane and in plane, or a coupled mode. It may not be a pure mode, depending on your structure. You take that value, and since it's an eigen shape, you unit normalize it with respect to its maxima, and you set that value at the maxima to the tolerance that is allowed, say 8 millimeters out of plane at the crown. So you set that unitized shape of the unity eigenvector to that value, and you bias the whole arch shape in that fashion. Okay, that's one at that point, given a unit value of what the tolerance says for the geometric impression. Then you do a nonlinear analysis. So it is just like a column. There is nothing like a perfect column. It is imperfect, and that's how you get your Young's modulus. You know, the same fellow who invented your Young's modulus that you see, Thomas Young, also built the whole theory of buckling of a strut and with the initial imperfection. So the same issues in an arch. It's an imperfect arch. It will never reach P-critical. It will buckle below P-critical, and its behavior will be nonlinear from start. Okay. Another thing in a very flimsy arch which you want to watch, which is a in-plane mode, is something called snap-through buckling. When it's a phenomenon that will happen in an arch. So these guidances you can get to some extent from Eurocode, the old British 5400 code, the Eurocode, and the specialist literature which you have, people like Bakker and others have written quite extensively on this. So you will get some guidance. There is guidance available. Anybody needing help, contact Alok, me, or Atul. We will be able to, Vinay will be able to help you with that literature. We'll give it to you. Right. I think if anybody has anything to say on the panel, thanks, Alok, for those lovely comments you made. Gopal, I think we should...
Thank you. Yes, sir, I will continue. Thank you very much, Dr. Harshvardhan Subbarao, sir. To all the panelists, to all the eminent expert and all, बस एक चीज कहता हूँ कि मतलब एक गुलजार साहब की एक बहुत पुरानी शायरी थी कि मिलता तो बहुत कुछ है इस जिंदगी में, मिलता तो बहुत कुछ है इस जिंदगी में, बस हम गिनती उसी की करते हैं जो हासिल ना हो सका। तो मैं सबको यही कहूंगा भैया कि जो अच्छे ब्रिज हैं उसके बारे में थोड़ा बात किया जाए, और अच्छे, मतलब अगर दिन में हम लोग इंडिया में दिन में ऐसा कोट किया जाता है कि 1 से 2 ब्रिज बन जाते हैं दिन में जो प्रोजेक्ट चल रहे हैं. So I will request IIB committee also that in our website, whatever bridges are inaugurated in daily or in a weekly, we should congratulate all the consultant and contractors and all, so that we can encourage the success of the bridges. So with this note, एक दो lessons और failures होते रहते हैं, and we should learn from them and we should not repeat. And with this note, again Atul ji.
Yeah.
Yes, sir. Harshvardhan Subbarao.
The Puri Saab is here, and Hegde, do you want anything to add? Any of you all to say a few words? Anyone? Puri Saab, Hegde, anyone to add?
Yeah. I just want to say that I know Atul Bobe for a long time. He's one of the engineers who can speak on the design as well as the construction aspect with equal eloquence. I think that he has put it once again today. And very fascinating and interesting presentation. I just want to know one thing from Atul. You see this, your basket arch bridge.
Handle.
What a two, compression member, arch member on top. It is three-dimensionally varying. Actually, it is not. It's like our signature bit. Out of the experience of signature bit, I'm talking about it. And the prefabrication of these segments are done in a segmental manner, as you explained, like a match casting of segmental construction. Then it has to be, fabricated in the casting yard, and after the casting yard fabrication, it has to be trial assembly. I'm sure that trial assembly would have taken place over here, there. Then it has to be erected. Some sort of a geometric control during the fabrication, trial assembly, as well as the erection has to be done. Yes. Did you have, and also another thing is between the two segments, what was was it a compression joint, or it's an arch, so it's always predominantly under the compression.
Yeah.
So perhaps, do you have a compression joint in the sense, was the machining surfaces were required, or you achieved it by way of the splicing, by the splices? I'm just curious to know that, because at that particular point of time, perhaps machining was not perfected to that extent. Perhaps you would have depended upon the splicing. That's what I feel.
Yes. So to answer your question, the first question was whether we did a mock-up. Yes. Unfortunately for Pavna, the mock-up photographs are not there with me, so you didn't see them in my presentation. Yeah. But yes, a complete mock-up was done. In case of the last bridge in Bhopal, you saw the mock-up. I did show photographs of the mock-up. So that's a fairly recent, bridge. And I made sure that our people took photographs of the mock-up. So we have the photographs now, and I can show them in the presentation. So of course, yes, you cannot do without a mock-up because this is completely three-dimensional. You cannot imagine it, even, and of course, when we did it 20 years ago, it was even more difficult because you only had AutoCAD at that time. You never had anything more than AutoCAD. And to translate AutoCAD 3D on ground was a hell of a task. I can tell you that.
No BIM or no Tekla.
No BIM, no Tekla, no nothing. To answer your second question about the joints, we did both in that time because we were not 100% sure about what we would be able to achieve physically on site. We butt welded those joints, 100% compression joints, and we added splice plate on top and we welded them also. So we had both in case of Pavna. We were not very sure at that time. So Pavna is a little, if you ask me now after 20 years of that bridge, the Pavna bridge was a little, I would say, over-engineered structure or an over-designed structure. I can say that. Probably if I redesign it today, I would probably put 5% less steel than what I did at that time. Of course, this comes with, I think, confidence of having had, done more than 7-8 cable stayed arches after that. But that was one of the first ones that we did. And to be able to do a three-dimensional arch at that time was really
absolutely
very challenging and very good achievement.
Extremely challenging.
Just to let the audience
should congratulate Atul for your 150 meters span. 150 meters span you could achieve with 1,000-ton steel. Yes. That is another achievement, I should say. Maybe because of construction technology, I think it was better compared to that of the first one. There, I think the construction stage was governing the design.
Yeah, correct. Yes. Absolutely right.
I think let's request Mr. Puri to...
Yeah. I think the final comments. And the concluding comments from S.K. Puri sir. Please, sir.
Thank you. I think in our road sector also, more and more steel structures are likely to come now because of, whether land issues or whether while the traffic is on and you have to construct such bridges. And these arch bridges are obviously, as far as the steel is concerned, the cheaper one. Since the codes are not there, what I would like to request is that, like we learn from the failures, let us start learning from our success stories. So if whatever we have done, if we can come up with some good papers on this, whether it is the design part or the construction part, methodology, so this will give, more and more readers will have, first the feeling has to come, first the kind of, confidence level has to come, because in the absence of any codes or guidelines, it will be limited to then few consultants only, and that also, so if we have to do it a mass scale, then because what I feel is that when this uh, uh, coastal corridors will come up, maybe 2 years, 4 years, 5 years. There, because of backwater, this 100-meter, 200-meter span will be a common thing of all the bridges. And we will require these such kind of bridges. And people now want signature bridges. Otherwise also, in the cities also, or whether it is metro. So I think it was a very nice presentation. I would like to say that I am going to take away from this, and in my profession as engineer, I'd like to see that wherever we can use that, and maybe we'll come back to you for some kind of guidance.
Yes, yes, sir. That's what this fora is for, Puri Saab. Your engineers and in ICT, most welcome to attend and learn and share with us. This is what this fora is for.
Yes,
I just want to add one point, which you all probably missed. The iconic crossing in Bombay, Bombay is made up of 7 islands. There is the Mahim Causeway Bridge, which Atul is designing, his firm is designing, and we are Proof Consulting. It started with stainless steel Avatar. It would have been India's first major stainless steel bridge, but the client shot us down with money. And then we came to various forms, and then we realized that constructability was an issue, and maintaining traffic on that vital corridor, which has 10 lanes, is very difficult. So it's a 10-lane, 4 arches that are now, the contract has been appointed and going for it. It will be beautiful and iconic right at the entrance of Bombay. It will be seen from everywhere if you come into Bombay. That's another fabulous structure that they're doing. And we're doing a 110-meter, my company Consumer is doing a 110-meter arch, quite similar to the bowstring, not so close, quite similar. But the construction technology there is also to be used is also very, very good. And we've borrowed actually from railway erection technology with a limited headway girder type approach over a creek which has mangroves. So we are not allowed to work on the floor. We had to work fully overhead for the launching. So that's another kind of constraint. And on that note, I want to also appeal to Vinay that we should have some topics. Venkat, you're here, Ramshila, you all designed, Stoop design, we proof checked. Consumer proof check. So I think that is another iconic structure which should be brought to this audience, Ramshila Bridge. Both the design and construction and also the contractors' points of view, etc. You would know best about that.
There was Ramshila and also there was Jia.
Jia.
100-meter span Ramshila, 120 meters Jia.
Parvati, yeah. Parvati.
But let me apprise you all that today when I'm seeing the comments that I've received, the appreciation that I've received on this question answer box, is absolutely fantastic.
Absolutely.
Maximum number of appreciative comments so far that I've seen today. So thank you, Mr. Bobe. Congratulations. And hearty thanks to you for sharing your time and experiences.
It's a pleasure.
And I think over to Dr. Gopal Rai for
to close
some of the formalities.
Again, the concluding part, मैं फिर से कहूँगा, पहले लोग अतुल सर को नाम से जानते थे, आज उनके काम से जानते हैं. Atul sir, with this line, I will request Swapnil Joshi ji. Swapnil Joshi ji is one of the project management consultant from Indento Associate. और ऐसा बोला जाता है जब वो किसी प्रोजेक्ट की प्लानिंग करते हैं तो प्रोजेक्ट समय से पहले हो जाता है. So refer to Swapnil Joshi. Swapnil Joshi ji is one of our Honorary Secretary for IIB. So I will hand over to Swapnil Joshi ji, and I think we should look for some project management talk also in future. We should hear from Swapnil. He has almost more than a decade experience in the project planning and execution, and he know all the Indian tip to how to execute faster project. Swapnil, over to you.
Thank you, Gopal. Thank you very much. So I would formally propose the vote of thanks for today's lecture. So first of all, thank you very much, Atul sir, for an excellent presentation. So you have taken us through a amazing film, I would say, with the first cable arch bridges, which are not these are non-conventional. On the 4 case studies of from basket handle river bridge over Pauna, then Kenagiri at Bengaluru, Goa, and Gopal, which ranging from 108 to 150 meters span. So wherein you have highlighted few very important parameters, wherein the for the basket handle bridge, where the methodology of fabrication, erection, and bringing the cables from UK with such a precision, wherein the software were not available, and still after 15 years it stands really strong. Then the bridge at Bengaluru, wherein you have given a very good example of where the bridge passing through the arch. Again, a network arch bridge. The bridge at Goa, which is unique in terms of launching and positioning of the arch, and steel bridge at Bhopal, which is 150-meter long and 30-meter high. So I would like to thank you for this knowledgeable presentation to all our participants, and a great valuable information for everybody. Thank you very much. Now I would like to thank our panelists for today's lecture series number 18, Engineer Rajiv Ahuja ji, Mr. R.S. Sharma sir, Managing Director, Sugam Technocrats Private Limited, for sparing the valuable time and giving the valuable comments towards this session. Thank you very much, sir, for both of you. Also, I would like to thank today's moderator, Dr. Gopal Rai, for moderating the session for this lecture series number 18. Now, I would also like to thank our senior members and EC members. Out of them, Dr. Subbarao, Engineer V.N. Hegde, Engineer S.K. Puri sir, Engineer R.K. Goel, Dr. Surya Prakash, and Engineer Alok Bhaumik. So thank you very much, all senior members, for participating for today's session and contributing to it towards its success. Now, I would like to give a big thanks to our Director General and President for motivating us to go ahead and take up some new challenges and come up with new patterns for dissemination of knowledge. Thank you very much, DG sir and President Vinay Gupta ji. Our team who drives these sessions, we are on the 18 series of lecture series 18, which we have done today. So the people who are driving this is Ruhi Agarwal from DGC, Engineer Deepika Singh from Intento, and Josefa, who is taking care of the complete IT solution and the digital platform. Thank you very much, team, for your great support.
And Swapnil, Preeti in the background.
Yeah, and Preeti. Yeah, Preeti for a great video. Thanks, Preeti. So it has changed the whole pattern, and the new thing is being introduced. Thanks a lot.
And so today's Lakshmi is Dextra. We should thank Dextra for sponsoring.
Yeah, that is the next one, which is the most important one. So for Dextra, I would like to thank a big thanks to Dextra's sponsor for today's lecture series, and we hope to get furthermore sponsorship for various topics and your participation towards the lecture. So thank you very much for your valuable support and promoting the activities of IIB. Thank you very much. And also, I would like to thank the most important thanks to all our participants, without whom this lecture series could not be a success. So thanks, a big thanks to all of you for participating and continuously being a part of the IIB lecture series. Thanks a lot. Thank you very much. Here we have tried and introduced a panel discussion in today's session. So for encouraging more and more interaction. So hope you guys have liked that, and we'll put up a different style of panel discussion again in the coming sessions. So thank you very for that. That is something which is very important, which we have introduced. And with this all, I would like to thank each and everyone. If I have missed somebody's name, for your participation and support to IIB's lecture series, and keep participating and become a member of IIB so that we can disseminate more and more knowledge towards it. So with this small vote of thanks, I would like to formally, Vinay sir, if nothing has to be You do have to say something, otherwise I'll formally declare.
No, please close. Only thing what I take from this is a lecture is considered to be, or a presentation is considered to be very good when the audience want one more of it. And when even the presenter wants to make one more presentation on the same topic, maybe with different experiences. And I saw this today. Thank you so much. Thank you so much. Really.
With this, I would like to
challenging,
formally declare
interesting.
today's session is closed. Thank you
Thank
very
you.
much.
Thank you.
Everyone.
Thank you. Thank you. All the panelists and all the people who have joined here, who I see on the screen. And please don't mind if I have not given you enough weightage or something. Thank you so much.
Thank you, sir. Thank you. Good night. Good night, everybody.
Good night.
Thank you, everybody.